Hi, in the last session, we talked about signal assignments in the combination process block, and we also gave a brief about the concurrent assignments as well. We discussed that what are the good design practices and why latches are not good for your digital system designs, and how you can avoid latches to create your VHDL designs. And we seen two ways to avoid them. The first method is to ensure that your output signal is assigned for all the possible branches in your combination processes. The second method is to use a register process instead of a combinational process if your requirement is not affected because of it. Now we are covering this register process block in more details in this section. So let's start. Remember that a register process executes based on a change in state of a clock signal or when a asynchronous reset signal changes. So this is our general template of a register process block. I will quickly read it first. So it is test process colon process reset comma clock begin if reset equals to 1, then d out gets the value of 0, else if rising edge of clock, then d out gets the value of function x1 comma x2 comma x3 up to xn, and if and process. So you can see that in this template only the clock and reset signals are included in the sensitivity list. Now if the reset is active, then we set the output d out to 0. Otherwise, the d out gets a value based on some xyz function on the inputs or signal, such as x1, x2, x3 here. This represents a generic register process where d out is driven based on input signal values or register process in this form. So, what does the hardware implementation of this process looks like? This is the hardware visualization of this process. Input x1 to x1 comes from the left, and the combination logic determines the value of the D out in the next cycle. Finally, the D out is implemented as the output of the flip flop on the right. We saw this diagram in the previous session as well, and this is really helpful to understand our signal assignments concept. Let's replace this general function with something more specific. So here I have replaced it with a simple two input AND gate. So now our D out is the AND operation between input A and input B. So our VHDL code will be test process colon process reset comma clock begin if reset equals to 1, then D out gets the value of 0. Else if rising edge of clock, then D out gets the value of A and B, and if and process. Remember, the process will only execute when signals in the sensitivity list changes. So in our case, the process executes when the clock or the reset signal changes. For now, let's assume that the reset signal is not active, means it is not applied. So now we only have the clock signal, and our processes will trigger when its state gets changed. Means when there is a rising edge on the clock signal, then our process will execute because the clock changes its state from 0 to 1. Similarly, when there is a falling edge on the clock signal, our process also runs because the clock changes its state from 1 to 0. Although the process runs on both the edges of the clock signal, but it only performs the useful operation on the rising edge, and it will do nothing on the falling edge of the clock signal because the else if condition is only true during the rising edge. So on the every rising edge of the clock, the signal D out gets a value based on input A and input B. Now let's look at the timing diagram and see how this circuit operates. Here is the timing diagram where we can analyze that how this assignment works. Because understanding these timing diagrams are very important if you want to do proficient in VHDL. I have also included a screenshot of our circuit just for the reference. So I have labeled the AND gate output as signal X. So now every circuit and signal has some name, so we can easily refer them to understand. First, assume that the reset is low, means it is not asserted. So because the reset signal is at 0, So it has no impact on the circuit. Now let's look at the clock signal. So we know that our process executes whenever the clock signal changes its state, whether it goes to high or low. From our VHDL code, we know that nothing will happen to the output D out at the falling edge of clock, right? You can clearly see this in the circuit diagram as well, because D out is driven by the flip flop, which is triggered on the rising edge of the clock, not on the falling edge. Therefore, D out can only change at the rising edge of the clock signal. In this timing diagram, the rising edges of the clock are numbered from 1 to 12. So we can use these numbers to refer to the specific clock edge. Here, signal A remains high, so we can ignore it for now. Consider this just to understand it, okay? So let's focus on the input B. So you can see input B remains low until the fifth clock edge, and on the fifth clock edge, B goes high. As a result, after some logical delay, the AND gate output signal X also goes high. The logic delay is small, so sig X goes high before the sixth cycle of the clock ends. So on the sixth cycle of the clock ends, the flip-flop captures signal X, which is now high. Therefore, just after the sixth cycle of the clock ends, our output T out also goes high. The important thing is to realize that the output signal D out changes after one clock cycle when the input B changes its state. Signals assigned in the register process blocks always follow this rule. So input B changes its state on the rising edge of clock 5 or after it, but the effect is seen on the output D out only at the rising edge of the sixth clock cycle. As a beginner, you may have little difficulty to understand these timing concepts just by looking at the VHDL code. But hardware visualization can make it easier to understand these timing variations on the various signals. So do not worry if you are an absolute beginner and if you feel difficulty to understand this at the moment, because gradually you will develop a picture of these concepts in your mind. But this is really important to understand these real hardware concepts for a good digital system design. So I recommend that always think in terms of a hardware implementation when you are writing your code in the VHDL. And this will make your VHDL design easier to analyze. Here is the another example. So I will read the VHDL code first. Test process colon process reset comma clock begin if reset equals to 1, then x1 gets the value of 0, x2 gets the value of 0, x3 gets the value of 0. Else if at rising edge of clock, then x1 gets the value of 1, x2 gets the value of x1, and x3 gets the value of x2, and process. Here I have three signals x1, x2, and x3. The reset assign all these three signals to 0. Let's see what happens after the reset is not applied. So whenever we have a rising edge of the clock, we assign x1 a logical one. Therefore, x1 will be high just after the first rising edge. The next VHDL statement is x2 gets the value of x1. So what do you think? Will x2 will get the logical one here? So you might think that x2 should also be 1 at this point because x1 is already 1 at this point, right? But this is not correct. Remember, x1, x2, and x3 are the outputs of the flip flops, and therefore they need to one clock cycle to update their state. So even though x1 goes high at the first clock edge, x2 will only change at the second clock cycle. This will become more visible when we look at the hardware implementation for this process. Finally, we assign signal x2 to signal x3 in the last VHDL assignment. Now let's see the hardware implementation and the timing diagram for this circuit and understand how these three signals get assigned the values. So here is our circuit, which implements the process from the last slide. So signal x1 is the output of FF1 flip-flop. Signal x2 is the output of FF2 flip-flop, and signal x3 is the output of FF3 flip-flop. In our code, we assign a logical one to the signal x1 at every rising edge of the clock signal. This is implemented by hardwiring the input of FF1 to the logical one. This way, on every rising edge of the clock, FF1 will get logical 1. Similarly, we assign the signal X1 to signal X2 at the flip-flop FF2, signal X2 to the signal X3 at flip-flop FF3. So this is very clear from the VHDL code, right? So this is achieved by connecting the output of FF1 to the input of FF2. Finally, we assign X2 to X3 in our VHDL code. This is implemented by connecting the output of FF2 to the input of FF3. Very simple. Now let's look at the timing diagram. During the first clock cycle, we see that the reset is high, meaning it is applied to the all three flip-flops. Hence, all these three signals are reset to 0. The reset signal goes to 0 after second clock adds. So afterward, flip-flops will start to capture input values from the third rising edge. Let's discuss that what will happen at the third cycle of the rising edge of clock signal. On this rising edge, flip-flop FF1 will capture the logical one present at its input. Now, after a small propagation delay in FF1, we see the state of the signal X1 changes from 0 to 1. On the rising edge of the clock cycle 3, FF2 will capture the value of X1, and the value of X1 at this point is still 0 because X1 only changed its state after some time of third clock cycle due to some logical delays, right? Therefore, on the rising edge, FF2 will still see logical 0 at its input and will capture 0 values. So signal X2 remains at the logical 0 during the third clock cycle. Same way, at the rising edge of clock cycle 3, FF3 also captures the state of signal X2. Since X2 is 0 on the third edge, X2 also remains 0 during the third clock edge. Now let's look at the clock edge number 4. So flip-flop FF1 will again capture the logical 1 at its input, and therefore X1 will remains at logical 1 as it was before. But now the input of FF2 will be at logical 1. This is because the value of X1 is high at the fourth clock edge, and therefore FF2 will capture a logical high on the fourth rising edge of this clock signal. As a result, we can see that signal X2 will go high just after the fourth clock cycle. But on the fourth edge, FF3 still sees a logical 0 at its input because X2 has not yet changed at this clock cycle. So FF3 remains 0 during the fourth clock cycle as well. Now let's look at the clock cycle 5. So X1 and X2 will remain at logical 1 during the fifth clock cycle. But the output of FF3 is now at logical 1. This is because signal X2 is at logical 1 during this fifth cycle clock. Therefore, FF3 will capture logical 1 on the fifth rising edge. As a result, signal X3 goes high only after the fifth clock cycle. So this is what we wanted to show you. In the code, we wrote the assignments to X1, X2 and X3 one after another. However, when this process runs, we see that the values of these signals do not change to logical 1 at the same clock cycle. So this would be the result when the circuit gets implemented in the real hardware devices. As I said, as a beginner, it might be quite difficult to sense the timing variations between these signals just by looking at the VHDL code. This is why I think visualization the hardware circuit is quite useful. In practice, the timing of these signals will be straightforward, and you will not have to worry about visualizing the hardware circuits. Here is the another example. In this example, I am assigning logical 1 onto the two signals called X1 and X2. So our VHDL code looks like this. Test process colon process reset comma clock begin. If reset equals to 1, then X1 gets the value of 0 and X2 gets the value of 0. Else if rising edge of clock, then X1 gets the value of 1 and X2 gets the value of 1, and if AND process. Again, just assume that we are not applied the reset condition. So here both x1 and x2 will go to logical 1 at the same time because this is on the same rising edge of the clock cycle. If you come from a software programming background, you might think that x1 goes high first and then x2 goes high after some time later because the code is written sequentially, right? But this is not the case with VHDL. Remember that VHDL is not a software programming language. It is a language for describing the hardware, and in hardware, X1 and X2 will go high on the same clock cycle, even though one statement is written after one another. Again, thinking back to the hardware circuit, which will make it easy to understand it. This is because both the flip flops for X1 and X2 have their inputs tied to the logical one. Therefore, on the very first clock edge, both flip flops will capture a logical one on the same rising edge, and X1 and X2 will both go to the logical one at the same time. Now, this is the last example for this video, and I want you to try to understand that what will happen if you have two assignments to the same signal. Suppose we are writing a code like this: test process colon process reset comma clock begin if reset equals to 1, then x1 is 0, else if at the rising edge of clock, then x1 gets the value of x2, x1 gets the value of x3, and if AND process. In this process, I have assigned x2 to x1, and in the very next line, I have assigned x3 to x1. So what happens then? The simple answer is that the VHDL simply ignores the first statement. Only the last statement will execute. So x1 will get the value of x3. Simple. And it will be treated like that the first statement never existed in that VHDL code from the hardware perspective. Okay, so that's it for today. I hope I was able to clarify how signal assignments works inside the register process. We discussed that how the VHDL signal assignments are quite different from the software programming languages like C or C++. Software programming languages tends to assign the statements sequentially, but VHDL tends to develop a hardware piece from your VHDL design, instead just the execution of statements. In the next session, we will be talking about variables in VHDL. We will talk about how to use them and where to use them and how they are different from the signals. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to our community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.